Problem 31 in section 4.3 asks us to show that the set of images of a linearly dependent set is also linearly dependent. So, we need to use the fact that T is a linear transformation, and so we're going to start off by characterizing a linearly dependent set, use the fact that T is a linear transformation, and then characterize our linearly dependent set of images. So, I'm going to start off by taking the given that the set V1 through Vp is linearly dependent. So since the set this is a terrible curly brackets. My curly bracket integrity breaks down very quickly. So the set V1 to Vp is linearly dependent. Here's the characterization of linearly dependent sets that I'm going to choose. The homogeneous vector equation will have a non-trivial solution. C1v1 plus CPVP equals 0 has a non-trivial solution. So, if we have a set of linearly dependent vectors, one is a linear combination of the others. That's a little bit harder to state in general. So I'm going to go with the non-trivial solution to the homogeneous equation version of characterizing linearly dependent sets. So since we have a linearly dependent set of vectors, C1v1 up to CPVP equals 0 has a non-trivial solution. What we're going to see is that C1 through CP is the same non-trivial solution to the vector equation with the set of images. To get there, we have to use the fact that T is a linear transformation. Since T is a linear transformation, we're actually going to get two things out of this. First, T of C1v1 up to CPVP is equal to C1T of V1 up to CPT of VP. And T of 0 is equal to 0. We get both of these things because T is a linear transformation. Since T is a linear transformation, T will respect linear combinations. The image of a combination is that same combination of the images. We also get that the image of the 0 vector is equal to the 0 vector. All because T is linear. Therefore, since C1 through CP is a solution to this equation, and the image of C1 to C1v1 up to CPVP is equal to 0, the image of C1 v1 up to CPVP is also equal to 0. Because we can't have a transformation mapped to the same vector to different things. So we also get that the image of C1 v1 CPVP is equal to 0. I should have included that in this second one. I need to fix it. I can't let it stand. So T of C1v1 up to CPVP is equal to T of 0, which is 0. That is what we needed to say instead of just this. Must be almost 10:30. So we'll use the fact that T is a linear transformation to pull out that same thing. Therefore, we can see that C1T of V1 up to CPT of VP equals 0 has a non-trivial solution. Therefore, that vector equation also has a non-trivial solution. Therefore, the set of vectors, the set of images, T of V1 up to T of VP, is linearly dependent. Any questions? And if you want to be fancy, this is a proof, so put all QED. QED. Now we're fancy. Any other questions in 4.3? So let's take a look at problem number 11. So 11, find a basis for the set of vectors in R3 in the plane x minus 3y plus 2z equals 0. Cool, I like this one, because this one goes back to the beginning as well. So some of you have been through Calc 3, multivariable calculus, and so you recognize this as the equation of a plane, but we need to connect that to planes that we've been talking about here. So good choice. So x minus 3y plus 2z equals 0 is a plane in R3. So we want to find so that means that it has to have a basis of 2 vectors. So it's a plane in R3. So it must be a basis. The basis must have 2 vectors. That is, this plane is the span of a set of 2 vectors, 2 linearly independent vectors. So if I look at this equation, the plane is the set of solutions to the equation. The plane is a set of solutions to an equation. So I'm going to use an augmented matrix of 1, -3, 2, 0. There's the augmented matrix for this system of equations. I'll find the reduced echelon form of this matrix. Oh, there it is. And we see there's a pivot right here under that corresponds to x. So here's x, here's the y, here's the z, here's the constants. So what we see is that x is equal to 3y plus 2z, or minus 2z, and then y is free, and z is free. So my parametric vector solution has the form x equals a y vector, which will be 3, 1, 0, and a z vector, which is -2, 0, 1. So here are the 2 vectors that'll be a basis for the plane in R3. -3, 1, 0, -2, 0, 1. Oops, scroll up. Because the plane is the set of solutions to this equation. That is, the plane is the null space of this matrix, 1, -3, 2. Any questions? For the most part, when you get to multivariable calculus, we change up how we describe planes. Instead of describing a plane with two vectors that form a basis for the plane, since we're in R3, we can say, well, we can get away with describing this as the one vector that's perpendicular to the plane. Then we only need one vector to describe the plane. So in R3, this DVD bonus material, we connect this to connect this to multivariable calculus. In linear algebra, we're describing a plane with two vectors in the plane. So I'm going to try to draw a plane. So it's the span of a set of vectors. Plane in R3 is the span of a set of vectors. So there's, in this plane, a vector u and a vector v. Let's say this is u, and here's the vector v. Everything in this plane is a unique linear combination of these two vectors. They're not on the same line, so they're linearly independent. But now, right now, our description requires two vectors. This description requires two vectors. So the way we describe planes in R3, since we're only dealing with R3 and we've taken up 2 as the basis, or for the plane, 2 dimensions for the plane, we'll just say, why don't we just use the vector that's perpendicular and say the plane is everything perpendicular to a normal vector. And so we're saying the plane is everything that's perpendicular to this vector. So we just pick a vector that's perpendicular to u and also perpendicular to v. So now instead of using 2 vectors to describe the plane is everything that's perpendicular to this normal vector. Plane is all the vectors perpendicular to the normal vector. Now I'm describing with the plane with one vector. I did. The origin's right there at u and v. I just didn't label it because it would have been too busy. Any questions? Remember, vectors are mobile. And so since u and v, that point that they're coming from, that could be the origin. The origin can be wherever we want it to be. Any questions? Comments? Snide remarks? Any other questions in 4.3? Cool. Let's pause the video on 4.3 and then we'll move on to, gosh, I wonder, how about 4.4?